So this is a question about using a video camera to calculate the acceleration due to freefall. The video camera is basically watching something fall in front of a ruler, and you have to explain how you can actually get to acceleration, g, using this setup. So release a steel ball in front of a meter rule. The ball drops in front of the meter rule. Use a video camera to record its motion. The camera captures 30 images per second, which may be played back one at a time. So for me, these types of questions, they often people often find them quite difficult. My advice is to always start with an equation. So if you're ever asked to explain how to do an experiment, then always start with an equation and work out from there how it could be done, how you could actually measure this. So in this case, we're doing g by freefall, so you need to look at your SUVAT and pick an appropriate equation. And there's a few appropriate equations in there. There is, you could use a equals v minus u over t. That's probably not the best one in this case, because actually you might as well have just used a different method to measure the final velocity. The best one in this case is actually s is ut plus a half at squared. So you could actually get all 4 marks by doing it this way, but I'm going to show you this method here. Now clearly u is 0, so we're actually not even interested in any of that stuff there. And you just got s is half at squared, and you've already got a mark for stating an equation that can be used. So how are you actually going to do it? Well, you're going to use the camera to frame by frame record the distance and time, and that's your first 2 marks actually. So you've said that the distance is measured, and state what you're measuring it with whenever you get these questions as well. For each frame. And this is the marked with a time base basically, which is the time between frames. So time is measured as time between frames, which is a 30th of a second, isn't it? And you can put that detail in, although you don't really need it. Okay, then you've got your mark here for your SUVAT and working out which one to use there. Well, now looking at this one here, how am I going to actually use this to plot a graph? Well, I need to plot, let's have a little think about it. I want a gradient with something related to A, so I can plot S against 2t squared. If you like thinking about this as y is mx. Okay, and that's your last one. How would you actually calculate that? And actually you could just have stated that you've got your range of values and you can use the equation to work that out. So I hope you're also remembering to have a little go at these before actually listening to me explain them. So just pause it now, have a go at them on a bit of paper in front of you, and then have a go and let me get you unstuck if you need to. So this one asks you to describe a systematic error. So you've got to remember exactly what systematic errors are. The errors in the system, errors that apply to every single result. So I think the most obvious one is that the camera is actually a distance away, and it doesn't see in perfectly 2 dimensions. Okay, it sees in like a cone, so there's distortion at the edge. So actually the camera introduces a parallax error. But there's other ones that are possible. For example, the ruler itself might not be perfectly vertical, so that would give you a parallax error as well. So you've got to say parallax and then ruler, or parallax and camera. it could be that the ball was actually moving before you started the video, or you haven't found the first frame correctly, so then u isn't 0, so your algebra doesn't work out. And there's another one which may be that the camera itself is not quite 30th of a second for each frame. In fact, I know my camera says 29.997 frames per second or something ridiculous like that when it's trying to do 30 frames a second. So that error is applied to every frame then. So one property of the steel ball that makes it suitable for the use, and I think this is the point, it's a ball. Galileo dropped 2 cannonballs and found that they fell at the same rate. He did not drop a hammer and a feather. They do not fall at the same rate. This is the worst hammer and feather I think has ever been drawn, because of the air resistance. So one property of the steel ball is that it's got a streamlined shape. Okay, so drag is as close to 0 as possible. Okay, I think that makes perfect sense to me. You could have had also that it's very dense, so that weight is much greater than upthrust in air. So let's do another spherical thing, which is very less dense, like a hydrogen balloon. Well, that wouldn't work very well, would it? Because that would actually go the opposite way and accelerate upwards. Okay, so it has to, that's one way to explain it. Fluids do have an upthrust. Air has an upthrust as any other fluid. So the weight is much greater than the upthrust, or the weight is much greater than the drag. In the case of the feather, the weight is only a little bit more than the drag, so it falls quite at a low terminal velocity. It also says, you could say shiny, so it's easy to see properly. And also you could say small, so that you get a precise reading. Okay, all of them kind of make sense to me, but I think that's the most obvious one, is that it's ball-shaped. Here we go with this last one on this question then. Explain an advantage of using a video camera to take measurements for this experiment rather than using a stopwatch. Now you'll be thinking straight away, stopwatches, yes I know this stopwatch has a human error boom time. I've got 2 marks on this. Hang on a minute, 2 marks for writing human error. Now you get no marks if you just wrote human error. What is the human error? What's causing the human error? Well, the human error is due to reaction time. You could even, nice and detailed, human reaction time is about 0.2 seconds, something like that. Okay, you didn't get a mark for that necessarily, but to explain it, well, what does the video camera do? It takes away the error due to the reaction time, and that reduces the uncertainty. And exam boards do like the word uncertainty rather than error these days, although that's fine. The error is the thing that's happened, and the uncertainty is the change in the measurement. There is a few other things that you could have said. The advantage, well, you can stop it and pause it, so your measurements are taken at exact times, or you can take longer to make that measurement. You can calculate more readings of velocity, so you get a more precise graph, if you like, more precise set of data. More readings for more reliability as well, you could have said. Also, you can repeatedly take the reading, so you can actually check and confirm your values, and that's acceptable as well. But I think the most obvious one is going to be, human error. The human error in using the stopwatch is due to the reaction time. Okay, hope this question helped. Let's go on to the next one.